Hello and welcome to CG5042. This is our next lecture, which is on corrosion. And there's an assignment on corrosion as part of the new assessments. So you will have received an email correspondence about that already from Erosion, just outlining what you have to prep. Just to understand and appreciate that the expectations for that are a bit more than just regurgitating stuff that is in the notes and in the slides. So you will need to read beyond the material that I'm covering here in this brief lecture, and also what's covered in the slides. So there's good resources online. If you do some searches, you can find some good archival sources for corrosion. And if you log in through the Glucksmann library, you'll also, if you do a search on corrosion engineering, you'll come across some books. The book I recommend is it's actually only in hard copy of the library, but there are PDFs of it available online. I'm not sure what the legality of those, but you can access versions of it. It's a book by Fontana called Corrosion Engineering, so Mars Fontana. That's quite a good book. But there are a couple of corrosion books available as e-resources through the library website. I've had a look at them. They're a bit heavier than what we need in terms of the content we're covering in this, because we're not doing a very detailed analysis of corrosion, but there is sufficient information in there. So whatever you do, make sure you're using an archival source, so someone who's put their name to it and they are qualified in what they're doing. Okay, so no point with a man in a pub with a dog, etc. Okay, someone who's qualified, has a PhD, put their name to a textbook, is published by a proper publisher, you know, the likes of Wiley, Elsevier, Springer, those kind of publishers. Okay. Right, so what are we going to cover? Well, there's kind of two sections to this, and what I'm not going to cover, I'm going to move through really fast, is this section here. I'll just mark it out on a tool. So the specific types of corrosion, I'm not going to cover in much detail, because that's going to be your own kind of private study that you will do that in. What I'm going to focus on here are the corrosion, the design process, the thermodynamic context for it, and I suppose the critical point really is this: the 4 points for for the 4 requirements for a corrosion cell. So this aspect here, so that's really important. Okay, you get an understanding of that, and then you can look at the different types. What you'll see is that with the different types, many of them have different names, and they're very descriptive because they're coming from, by and large, observation. So they're coming from experience in service. And if we look at pitting corrosion and crevice corrosion, for example, you'll see that the mechanism of attack is actually pretty similar. Galvanic is its own distinct category, so we'll give a brief mention to that. And there's some other kind of material-specific ones as well. Okay, so in essence, what I want you to do is be able to read over this stuff yourself. You'll select one of these as part of your coursework and write a detailed analysis of that for one particular unit operation. You know, so I'm going to focus, as I said, mainly on the first 3 bullet points here. Right. So, what is corrosion? Well, what it is the removal of material or an alteration of the material properties. Because when you do design, you're choosing the material for its performance. It's got strength, or a certain feature that you want. And what corrosion does is that it removes that material, strips it away, and it also not necessarily strips it away, but makes it unavailable for the intended design use. So if we link back to the reliability slides where we had the strength distributions, when you look at those, what corrosion does is it weakens the strength of the material as a function of time. Okay, now there are many different types of corrosion. So we've got here wet corrosion, dry corrosion. We're going to talk about metals primarily in this, but bear in mind that non-metals can also be attacked. And corrosion can occur on both the environmental side and also on the process side. So it may be your process fluid, or it may be the ambient air as well. Bear in mind that those things can change over time as well. So, for example, if you build a plant, typically chemical plants, they're located in specific geographic regions. So in Ireland, if we look at Cork, for example, there's a particular region in Cork where there's quite a lot of chemical process industry is centralized. Similar in places worldwide, China will have particular regions where they have a high concentration of the process industry. And what you may find is that your environmental conditions may change arising from the atmospheric quality due to emissions of plants there. So you may, when you're designing, want to look at the pipeline of what is planned for the process industry in that region, and what are the expectations regarding, for example, air quality, because that may change your environment and change your rate of attack as well. Now, what corrosion is it's very multidisciplinary. So we're covering physics, metallurgy, electrochemistry, and engineering. Most people aren't familiar with the electrical aspect, but we'll come to that in a while. And one aspect is, of course, that it doesn't look nice. And from a design point of view, that can be quite significant, because one of the things you want to have is that the public have confidence in your design. If you take the example of the nuclear industry, when you're processing nuclear material, you don't really want them to see the public to see lots of rusty pipes. Now, rusty pipes can be perfectly safe. I would say you can build in a corrosion tolerance into your design, and you factor that in, the rate of attack. So it's not a concern. So things can look quite rusty, but actually be perfectly functioning and meeting the design requirements. And you factored in the life of it, but just someone looking at it, they lose confidence in it. They feel, okay, it's rusty, and it's deteriorating, it's not fit for purpose. So in certain circumstances, you may want the place to look sparkling and tidy and nice to convey that sense of, something that is very much under control. So, typically as engineers, we ignore aesthetics and we focus on function. But this aesthetic aspect can be quite significant in the process industry, where you will want it to look good, just so people have confidence, or appear to have confidence in design. And you'll see this with aircraft as well. If you get onto an airplane, they make the aircraft look nice, they clean it, and then you think that it's nice and safe. Whereas you mightn't see the cracks underneath it and stuff like that. They're there, and the aircraft is perfectly able to function with them. Right. So that aesthetic aspect may be a factor, but outside of that, it's a high cost where you're losing material. It's material you've paid for. It has a function, and it's being removed or modified from its original intended state. And as we mentioned there, it increases the hazard rate. So we get that linked to the end of life in the bathtub curve from the previous set of lectures. So really identifying corrosion, predicting it, identifying what the rate of attack is. Okay, so being able to understand at what stage do you need to do inspections, what can you do to mitigate against it, is a key element of the design stage. So it's a very important aspect of that. So it's important you do have an understanding of corrosion or the materials that you're looking to use. And design really plays a huge factor in this, not only in terms of the shape, but also in terms of the materials that you can use in the particular environment or process fluids that are being used. So what are the consequences? Production shutdown or failure, so that costs money. Increased maintenance, again, that costs money. Compliance with consumer or environmental regulations, so in terms of the integrity of your product and the effects that may have on consumers, especially from the pharma sector, for example. Environmental regulations, so you're impacting on the air quality or the local environment. Product quality issues there, which I mentioned. Greater fuel production and energy costs due to lost material, and you need additional working capital and larger stocks. Okay, so corrosion costs a lot of money, and there are stats out there that you look at the annual cost of corrosion in terms of the different sectors, process sectors. I used to have them in this, but they went out of date too quick for me to. One of the challenges with corrosion is that there's a perception that you may have that it's possible just to eliminate it. And what we're going to do is we're going to look at a thermodynamic understanding of what corrosion is. And hopefully what that will show you is that you would accept that corrosion is inevitable. It's something that's going to happen. And what you want to get control over is the rate at which it progresses, so the rate of attack. And factor into your design process how you're going to handle with it. So don't go in with the perspective that you're going to stop it. Go in with the perspective that I'm going to identify what's going to happen and try and minimize the rate of attack. So where this whole perception comes from is really looking at the entire life cycle of a material. And if you look at the materials that we use in service, so the metals and the alloys, they're in a thermodynamically unstable state. So what that means is that you don't, start digging in a field and come across a stainless steel that you can, reshape and machine. So all the metals and alloys that we have produced have come from an ore state that has been processed, and quite a lot of energy has been put into it. If you think of, a steel works, for example, the amount of energy that is consumed in producing the material. So from a thermodynamic perspective, what we've done is we've taken a material and we've put a load of energy into it. So we've essentially increased the internal energy of that system. And what corrosion then is the natural deterioration of that material or the reversion of that material back to its original state as an ore. Really, this is what Fontana describes in his book, is that corrosion is extractive metallurgy in reverse. I think it's a very nice way of getting to appreciate what corrosion really is. So if we look at this slide here, we have a timeline where on our reaction coordinate down here, we've got the ore state, and we put in a lot of energy to bring it up to the metallic state, which we're going to use. And then we have it in service, and there's a tendency for that to revert back to a corrosion product. So it's minimizing the energy. So for a corrosion reactant to occur spontaneously, there must be a reduction in the free energy. So what we can do is we can look at the free energy for a material in a particular environment. Typically, these are aqueous environments, so there's water inside there and oxygen. And that gives us an insight into whether or not corrosion is likely to occur. Now, it is important that it gives no rate information. So if you recall, the thermodynamics deals with inlet and outlet states, initial and final stages, state 1 and state 2. It doesn't give rate information. So it just tells us whether something is likely to occur or not. Okay, so if we take some simple reactions here, we've magnesium, and we've got a negative here. We've got copper, and it's got a negative. And then we have gold, which has a plus. So what that tells us is that the reactions involving magnesium and copper are likely to proceed in a water and oxygen environment, whereas the reaction with gold is unlikely to occur thermodynamically. And again, that's something that we can observe. If you dig in the ground, it is possible to find gold in its pure state. Whereas if you dig in the ground, you're unlikely to find copper or magnesium. So they're more in an ore state and had to be processed to extract the metal. Now, one of the features of this is that once it tells us about the propensity for the reaction, if we look at copper, for example, copper will corrode, but an interesting feature of copper, and if you walk around the campus, or obviously we're all shut out from it at the moment, but there's quite a lot of copper clad onto the buildings. For example, the library building or the Schrodiner building has recently just has got quite a lot of copper on it. And if you're in the city, St. John's Cathedral has a copper roof. And what happens with copper is the corrosion products adhere onto the surface, and they form a protective film. So this is referred to as a passivating layer. So although corrosion occurs, it occurs on the surface, but the corrosion product remains adhered to the surface, and it actually protects the surface from further attack. It shields the material from the environment. And that's something we'll come back to later on. So you will find materials that are passive in an environment that the corrosion does occur, but the corrosion products remain quite well attached to the surface. Whereas if you take, iron, for example, and rust starts to form, the rust flakes off. So the corrosive attack, the reactions continue. So again, I suppose our key point here is that with the thermodynamic perspective, we don't get rate information, but it helps us kind of formulate that concept of corrosion being something that is inevitable. And what we want to focus on is identifying the appropriate reactions and minimizing the rate of attack. Now, the corrosion cell. So this is how corrosion actually occurs. And what it involves are ionic and electrical exchanges between the material and its environment. And by the environment, we mean either the external environment. So if we take a pipeline, for example, the ambient air, or maybe on the process side of it. So the fluid side of the pipeline, the internal side of it as well. So you can have corrosion occurring on both surfaces. Okay, so that's something to bear in mind. Don't just focus on one, consider both in your design. And we've got 4 requirements. We have the ionic path, electronic path, an anode, and a cathode. And people tend to focus on the chemical side of corrosion and kind of forget about the electronic side of it, the electrical side of it. But all 4 of them are necessary. Okay, so what we have is in the material, we have the anode, the cathode, and an electronic path established. And then in the environment, we have the ionic path. And this is referred to as a corrosion cell. And each of these 4 things are necessary for corrosion to occur. And if you knock out one of them, or any of them, corrosion stops. It can no longer proceed. So you'll find that one of the strategies that people do is they will put in a passivating film. So they'll try and put a coating to isolate the surface from kill that ionic current path. Another strategy that you may come across, and it's kind of a surprising one, is well, you try and interfere with the electronic path. So you try and break that if you can. It's distinct materials. So in galvanic corrosion, you'll see that approach. Or put a voltage on it. So apply a voltage to the material side of it to try and interfere with this electronic path. There are strategies that you may come across. But this corrosion cell, it may be stationary, in which case it's more straightforward to interfere with it. But can also be dynamic in that they move locations around the surface. So these are reaction cells that are occurring and they're moving randomly around the surface of the material. So the anode is where the corrosion is visible as loss of material. So this is where you think the corrosion is occurring. And again, it is just one aspect of it. So it is where the metal ions go into solution, so you're dissolving your material. So you have zinc forming the Zn2 plus ions, you're releasing 2 electrons, aluminium AO3 plus, and general M gives us Mn plus plus N electrons. The cathode is where the electrons are consumed. And again, you don't have visible sign of corrosion here, but there may be a visible coating or a deposition occurring. But the reactions that are occurring here are equally as important as those that are occurring at the anode. Okay? So here we have the electron consumption, okay? So we're forming that. The electronic and ionic paths are what close the circuit. So the current flows in the form of ions in solution from the anode to the cathode via the ionic path in the environment. So as I mentioned, it may be the external ambient environment or the internal process fluid. And the cell is closed by direct current in the metal. So that's the electronic path. Okay, so we have those 4 things. And essentially what you have is a balance between all 4. So really, one of the things to bear in mind is that if people tend to focus on the anode, but you can do things to the cathode that can drive the current up and increase the density through the anode and increase the rate of attack. So there are things you can do that can be really detrimental to what you want or what you expect. And there may be happening things away from where you think the corrosion is occurring. Because the whole cell is set up by these 4 things. Okay, so these are our 4 requirements. We've got metals going into solution at the anode. That gives us the material loss and the visible sign that corrosion is occurring. Current flows from the anode to the cathode through the movement of ions in the fluid. So that's our ionic path. So that may be the external ambient environment or maybe the process fluid as well. And at the cathode, we have electrons are being consumed. Then the electronic path through the metal completes the circuit. Again, as I mentioned, the rate of corrosion is dependent on the balance of all 4 aspects. And if you start to interfere with one of them, you can have a dramatic effect on the rate of corrosion. So as I mentioned, strategies include protective films, appliance of voltages, introduction of sacrificial anodes. That's a nice one that is used in galvanic corrosion. So you put in a material that forms a new anode. So something that takes up the role of an anode. You put that in, and that has no function other than to be eaten away. And you know it's going to be eaten away, and you're happy with that. It has no structural function, for example. Another thing is the use of inhibitors for the ionic path. So if you're on the process side, for example, you'll find in heat exchangers that they'll put in corrosion inhibitors into the fluid to help reduce the corrosion deposits. And corrosion deposits, for example, in a heat exchanger can seriously interfere with the thermal transfer, and again reduce the diameter of the pipes or the channels for the fluid to flow through and drive up the pressure drop considerably. So that's something that we'll mention again later on. Now, something that's also important to mention, and I mentioned it earlier in terms of the use of these protective films. If we go back just to the slide here. So if we put a coating over the surface here, and we then shield or we have a passivating film. So for example, the corrosion products form that passivating film. So either or we painted the surface or did something to isolate the surface from the environment. So ostensibly that will, sort everything out and really kill the rate of attack. In fact, in principle, it stops it completely. But very often what can happen is that you get damage to the surface. So we get some sort of a dent in it that the corrosion product is removed or the paint is stripped or damaged in some capacity. And our anode is extremely small, but if we have a large cathode that has taken place somewhere else, it will drive a very, very high current through this and can lead to an accelerated rate of attack way beyond what you originally envisaged. And again, bear in mind that your thoughts are, well, now I've got to paint it, sure the surface is protected. And if any of you are fans of the kind of Discovery Channel, there's various programs in it you can watch. One of them was on the Golden Gate Bridge, where essentially they never finish painting that bridge. As soon as they've painted it, they got to go back and start all over again, just to protect the structure from corrosion. And if you look at those kind of disaster programs that go on about, what happens if humans suddenly vanish, and they kind of show how our mega structures will rapidly deteriorate and collapse due to the lack of maintenance on them and the corrosion that can occur. So just by putting in a film doesn't necessarily mean that you get protection from it. You may, if there's any damage, have a very concentrated space or flux, through the anode and have a very high rate of attack from that. Another feature that may occur with damage is you may cause crevice corrosion, and we'll mention this briefly as we slide through or move through the slides. That in crevice corrosion and pitting corrosion, you have a change locally in the environment where corrosion is occurring, and you get a very high rate of attack because you have a much more aggressive environment. It's a microclimate that is established inside a confined region. And again, if you have a damage in this and corrosion starts to occur, you have essentially a little thin layer will open up of whatever 100 microns, whatever, small gaps, and inside there you have different mobility of ions, and you get a localized change in the environment, and you get a very accelerated aggressive attack, again way faster than what you expect. And this may be occurring underneath the paint surface. So you got damage somewhere, it's in the seat, and then it's progressing and eating away material. But when you look from the outside, it seems perfectly fine. So Corrosion, it can be quite an insidious thing. Now, so that concludes the bit on the 4 requirements. So we've covered the thermodynamic aspect to it. So looking at the free energy as whether corrosion is likely to occur or not, and our 4 requirements for a corrosion cell. And the next bit, and we go through a whole series of different types of corrosion. And these are quite descriptive, and I'm going to refer you to a textbook for that. So I do need you to do your own reading and research into this in your own private study time. Okay. And what I don't want to see in your assignment is simply regurgitation of my notes. I expect you to read beyond the notes and inform yourself. Use these slides and this lecture as a starting point, just to get you running on it. We can see here some examples of uniform corrosion on some piping, and it doesn't look great, but it's not a concern. We build in corrosion tolerances into pipes for uniform corrosion, so we know that we have our thickness, which we will do according to standards. We'll figure out the pipe thickness. We'll design that. That will be to a known standard, whether it's ANSI or a European standard. And we factor in then a corrosion tolerance. So you put in material that gets essentially eaten away. When you look at it close, you can see that has that mottled surface. That is the material as it flakes off, and there's deposits on it, etc. So that's not really a concern. So we've got uniform penetration over the entire surface. You've got local corrosion cell action, so multiple anodes and cathodes that move about the surface, so that it's not a static event. Greatest destruction per tonnage, but really easy to see. You just see the damage there. And you can figure out the rate of attack from immersion tests. So you put some material out on site, and you measure the rate at which it's corroding. And then you factor that into your corrosion allowance. Okay, so that's as much we'll say in that. The more insidious ones then are things like pitting corrosion. And again, now if you look at these, what we're seeing is it is a highly localized corrosive attack, and it's accelerated compared to uniform. So you may have uniform corrosion, for example, occurring on the surface here. Very often it may mask that, so it's harder to see. What you have is a narrow, deep void. This one, you can kind of, it's larger, this is wide and shallow, it's not much of a concern. This one will be a concern, and this one. Because if you look in from the outside of this one, it's very hard to see that. And again, it may be masked with corrosion products, but there's quite a lot of loss of material, subsurface cutting there, again with this one also. So that's why it's referred to as an insidious form of corrosion. And crevice corrosion is similar to that. So what happens is that you get, essentially, I'll summarize it here, that we have a microenvironment, a microclimate that is set up inside here that is really aggressive and not good for the material. And here we have a passive film. So we're getting, due to this barrier here, a change in the motility of ions going through. So we get a change in the local environment that gives us accelerated attack. And again, chloride ions here can be quite bad for this. Okay, so again, pay attention to what may be in the environment or may arise in the environment in future. Again, the concern here is that we got failure with minimal loss of material. So now you're being perforated with very little loss of material. If we go back to the uniform corrosion, you can see it, it's there happening, it's happening at a uniform rate. You're sure a certain distance in, it hasn't progressed, it's only on the surface, and then that's falling off, and it's making its way through the material as it eats away at it. Whereas this is making damage, it's getting in deep, and it may penetrate the whole way through your material and cause you a failure with very, very little sign of it. So again, how do you spot that? How do you send people out there? Can they easily spot it? So there are challenges around that. Crevice corrosion, again, it's called crevice because it was found in crevices. So again, if we look at the slide here, underneath the washers. So they remove the washers, everything looks fine on the surface. A bit of pitching going on there in the corner where there's that weld. But underneath the washers, then there is corrosion taking place. So again, it's insidious. And it has a similar mechanism of attack. We have this crevice, so stuff seeps in there, it is held in there, it stagnates. And again, thinking of stagnant flow regions, things where stuff can accumulate, is generally bad news for from a corrosion perspective. So in your design, you want to design stuff that they drain out quite easily. So there's no kind of there's no areas where the flow will grind to a halt and just the fluid will sit there. And you can see in this crevice, stuff will sit in there. It's not going to move out of there. You get this change in the local environment and you get an increased rate of attack. Okay, so again, that's quite insidious. If we look at tuberculation, it's considered a type of crevice corrosion. You can see the outside of this pipe here looks absolutely perfect, no real concerns, but the inside has been compromised. And if we look at the diameter of this, you can see that it's, the open flow area is substantially reduced. It's about 1/3. So you've got I think doesn't really write very well up in that. But in terms of our open area for the flow, well, it's what 50% reduction. So it's at an angle there, skewed. So you've got a 50% reduction in the diameter. Now you might think, well, so what? But you can see when we're designing piping systems that you'll design this diameter to be optimum, and it will be tied to your selection of your pump. So your pump behavior and your pump efficiency will be linked to the size of your pipe diameter and the flow resistance going through it. And if you decrease this diameter substantially, you have quite a heavy influence on the flow rate. So if we take it that the flow rate is constant, the pressure drop is proportional, if I can write it here, to 1/d to the power of 4. Okay, so it is extremely sensitive to it. And when we look at the work required to pump, okay, so you all notice, of course, that the work required to pump a fluid, how much energy does it take to pump a fluid through a given pipe, is the flow rate times the pressure drop. So our pressure drop, if we've halved the diameter, so we're going to see a substantial increase in the pressure drop. So our work that our pump has to do, our energy consumption, is going to increase significantly. And furthermore, and when we get to the pumping section, you'll see that you'll have designed your, particularly if it's a centrifugal pump, you'll have designed it to be working at a particular sweet spot in terms of efficiency. And if you change the resistance of your system, which would happen here, you end up shifting that off its ideal operating point and best efficiency point. So that means your pump is working less efficiently. So on top of this, your actual electrical work is linked to the efficiency of the pump, and that will change. So how we do detect that? Well, in this case, putting pressure sensors regularly on the line, you'll see a change in the pressure occurring over time. And that will indicate that there is a blockage forming, or you may be able to detect it in your pump and then try and troubleshoot down through the system to see where the issue is. Okay, so again, this is quite insidious. You can't see it from the outside. Galvanic corrosion, I mentioned in the introduction, is quite an interesting one in that it's driven by a potential difference. And if we look at the examples up here, we've got two dissimilar materials, and very often it's called dissimilar metal corrosion. So one of the materials here, you can see the nut on this is taking a lot of damage. We see this pipe here is taking a lot of damage, and here the nut is perfect, and all this material here is taking a lot of damage. The threaded part of it, the outside part of there, the external surface here. But on, well, if we take this example here, this one is become the cathode, and this one has become the anode. So you've got up with the dissimilar metals, one of them has taken on the role of the anode, and one has taken over the role of the cathode. Okay, so the noble metal provides a site for the cathodic reactions, and the base metal provides a site for the anodic reaction. And we can look at the Galvanic series to decide or help us select the materials. So, for example, if we've got an aluminium alloy up here, and we're using, we'll go with, say, Hastelloy. Okay, just choose that as a material. So having a design that is using aluminium alloys and Hastelloy is a bad design choice because they are quite far apart on the Galvanic series. So if you use that, well, one of them is going to take up the role of anode and the other is cathode, and you will lose your material. Okay, so the aluminium will become the anode and the Hastelloy will become the cathode. So what you want to do is try and choose ones that are close together. So if we take a 400 series steel with, you know, say brass or something like that, you know, they're closer together, so you're much less likely to have that reaction taking place. Some of them are not very intuitive. If you look at the, say, the 400 series steel and the 300 series steel, so you can see that the, you know, if you take a 316 stainless steel, that will become cathodic if it's connected with 400 series steel. So again, your choice of material becomes very, very important in this. The other thing you can do is you can interfere with the electrical connection between the two. So if you put in a piece of material that isolates these, put a coating on this, you may interfere with the electronic path and that would stop it. Now, there's a very interesting article online that if you do a search, you'll find it on the Royal Navy and how they discovered galvanic corrosion. And there's some examples of it that they discovered in, you know, very early ships back in the 1700s and up into the 80s in the Falklands War. They had nose reels of the Harrier jump jets were collapsing, arising from galvanic corrosion, something that they discovered and knew, had a pretty good understanding about back in the 18th century. So there's some health warnings there on galvanic corrosion, just in terms of using the Galvanic Series. But really your material selection and interfering with the electrical connection are the two main strategies that you would use. Would gloss over things like erosion corrosion. That's where your processed fluid and particulates in it are destroying things. You will find things like where it bends inertial regions in the flow in particular. So where there's a change in acceleration, so on the bend here, for example, fast moving parts where there's a change in momentum of the fluid. So the impeller is striking the fluid and imparting momentum to it. So again, there's a lot of inertia associated with that transfer. So you will see the impeller is what's destroyed. So essentially your pump gets chewed away. So it's not particularly nice in that regard. Again, fretting corrosion, that's vibrations between struts. You can have a look through that. Then there's ones that are occurring inside the material itself. So very often we make alloys for particular properties. We put materials, mixes, and recipes of different additives into pure metals to give us particular properties and particular strengths that we wish to use. And corrosion can be set up, corrosion cells, can be set up between the components, the constituents of them. So again, there's a bit of detail on that. Exfoliation is tied to aluminium. And again, you see that kind of flaky material. Dealloying one is, again, it's another insidious one. Again, you've chosen the alloy for its properties. And what's happening here is that you've got selective dissolution of it. So you're essentially, one of the alloys is being stripped out. So you're losing all of that. And a typical example of this would be the graphitization of cast iron. So you're left with kind of a matrix of graphite in there. It looks like it's been deposited, but what has happened is that the cast iron has actually been stripped out of it. Dezincification of brass. So again, the material essentially de-alloys, it undoes the mixture that was created. Okay, stress corrosion cracking, again, requires a tensile load. And obviously to lose that, stop that occurring, you just lose the load, but it's not that straightforward. You'll have loads from welds, residual stresses, thermal loads, for example, thermal stresses may be applied. So again, it's not straightforward just to say, well, we won't cause any loads. So again, you can read up some more on that. There we go, SAC, a bit of discussion on that. Hydrogen embrittlement. Again, I'll let you guys read through that. And then we get on to the corrosion prevention strategies. So really this is tied back to this concept of the corrosion cell, and what you're trying to do is to interfere with one of the elements of the corrosion cell. So with uniform corrosion, a typical strategy is you say, look, I'll just get over it, and I build on corrosion tolerance, and I'm not worried about it. You may not want to do that if you'd like it to look nice. So you may paint it, or just put in some kind of inspection. But very often, if you paint it, you may increase your rate of attack if the surface gets damaged. Use metals and alloys with high purity that are not susceptible to corrosion. So again, proper selection of materials. Use the coatings. So I mentioned there about damage to the coatings can cause problems. Corrosion inhibitors in the process fluid, again, to try and change the environment. Cathodic protection, so sacrificial anodes or apply electrical voltages to make the material a cathode. Okay, so you interfere with the electrical path as well. Best thing you can do really is design, good design. So design to minimize the corrosion problems. So avoid stagnant regions. So when you're putting in designs, if you're draining a tank, for example, we have a tank like this and we have an outlet here. What you want to do is to have a tank more like this, that's U-shaped, and we have the outlet down the bottom, so it's free draining. Okay, so here, not going to cover this. I'm limited in terms of what I can draw. This one here is bad, so we'll get that on X. And the other one then is what will be good, because you're having a free draining surface, free draining exit here, whereas this one you have a stagnant region. So no matter what you do, you'll always have material down the bottom, and it will sit there, and you have an opportunity for the reactions to it. So again, avoid thermal gradients, where you may form condensates from the environment. Avoid bends, or if stuff is going to drain, that stuff doesn't pool in particular regions and things like that. So there's a lot of design stuff that you can do that will improve your corrosion susceptibility. An example I can use from aerospace, where they use these J-bolts, J-beams. They use these to support the floor of the aircraft, which is where the passengers are. And they have this kind of a J shape. And what they found in a particular type of aircraft was that they were getting savage corrosion occurring down here. And it was underneath the toilet in the galleys. So in the toilets and the galleys, it's very hard to stop leaks. So the various fluids were coming down, they're pouring through, they drip down, whatever, and they would accumulate then in these portions of the J-beams. And again, these shapes are there because they have particular strengths, and in aircraft, the design is optimized based on weight. So they really want a minimum structure there that is as strong as possibly can. So they were losing part of the strength of it, and there was a risk that the floors would collapse. In that case, they never really designed that this thing would occur. It was only occurring in specific regions. But what they had to do was they had to replace these beams in the aircraft as a maintenance step, and it proved a challenge for that manufacturer to actually produce sufficient stock of spare parts to be able to send out to the maintenance stations to perform this maintenance on the aircraft. So a simple thing like just putting a hole in there and making sure the material is strong enough even with the hole to allow the thing to drain out would have solved that problem. So there are some straightforward things you can do in your design, and clever things you can do in design to help minimize and mitigate against corrosion. Now, the last slide, I'm conscious that this is a 45-minute lecture at this stage. It's just a bit of a chat on the surface coatings. So we've got different types. We've got the examples of them, the advantages and the disadvantages. And really the disadvantages are associated with damage to the films, to the coatings. And there you run the risk of accelerated attack. So sometimes you may be better off not to go with it, or to build in a regular maintenance interval that if we go back to the example of the Golden Gate Bridge, they're constantly painting that structure to protect it, to maintain the correction. Okay, that concludes this lecture on corrosion. I've covered quite a lot of material. Usually this would take me kind of 3 lectures to do. We'd usually in class spend a lot more time on it. Owing to the shutdown, what we've done is gone through the introductory stuff, and I'm directing you guys to expand your reading, read over the slides that we have on the different types. You select one particular type of corrosion and you write a bit of detail on that and research that further with a view to a chemical process. Okay, so that's the whole idea with the assessment for that. So it's something essentially a self-directed learning that we initiate you, and make sure you're using archival sources for your information. If you have any questions on it, just come back to me. The resources, again, Fontana, you can get versions of that online if you can access them. I was able to find a PDF. Unfortunately, I can't upload it because I'll be violating copyright. But there are corrosion books available in the library that are accessible as e-resources. So again, have a look at those. Pick whichever one you feel is interesting to you, and look into that in a bit more detail. Okay, thank you for listening. I hope you found that useful, and come back to me with any questions or queries.